All right, gang, so for this video, let's look at what happens when we pick all those Lewis symbols and stick them together. The resulting structure is called the Lewis structure, right? And that's all it really is. You're just taking, it's like taking little, Lego pieces. You take that Lewis structure, that Lego piece, then go dunk, 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 stick them all together. But we have pretty specific rules for how they can go together because, again, the overriding goal is to achieve a noble gas electron configuration, or each atom is isoelectronic with the nearest noble gas, so it has 8 electrons for anything in n equals 2 or higher, thus the octet rule, and 2 electrons for anything in n equals 1, called the duet rule. Right? And I'm also going to throw in there, we want to achieve the preferred number of covalent bonds. We're talking only for Lewis covalent structures from now. Now, this is true for ionic and covalent, but we're going to focus these rules for covalent species starting on. So once you connect them all, you get the Lewis structure. If it has an overall charge like the ammonium ion, the NH4+, we put brackets with a little plus charge. And that represents, if it's negative, that means we have some extra electrons in there. If it's positive, we lost some in order to attain noble gas electron configurations for everything. So let's look at some rules. The ones I'm going to use for my class are out of your GCN, not out of your textbook. So a little non-traditional, but the way that I like to teach them is so that you can predict if you got any weird things going in ahead of time, whether you have any multiple bonds, double or triple bonds, if you've got anything that disobeys the octet rule. Life's always not so nice. So the way I'm going to teach you allows you to predict that stuff ahead of time. You can predict whether you have an organic ring structure in there, like a hexagon or a pentagon. It's pretty cool. But the more traditional way doesn't do that. Maybe a little bit easier, the traditional way, but I like the predictive capability of what I'm going to show you with these steps. But they overlap a lot. So whatever way works, but at least if you got me, please use the steps that I'm going to be teaching you. So when we're going to be doing Lewis structures, what we want to do is figure out how many valence electrons that species has. I call it the ante, the pot, right? So, one of my great friends is a professional poker player. And so when he goes and plays Texas Hold'em, right, everybody has to put an ante in, or, well, it's a little different because you got blinds and all this stuff. But so when we go play with him with all our friends and he takes all our money pretty much, we all sit around the table and we got our, our coins or whatever, and we have to put, say, a quarter ante in there. So say there's 6 of us, we all put a quarter in there. And then there's 6 quarters in the pot. Okay? And then we make our bets and play the game. But either way, if you look at just that, let's say nobody bet after that, there'd be 6 in there. Let's say you won the hand. You take all 6 of them. You don't care where those quarters of that money came from. Oh, that came from Mikey. That came from Mike. That came from, it doesn't matter who it came from. You just go, it's all mine. That's how I vision a species, right? So if I had the ammonium ion, you got the nitrogen and the 4 hydrogens. Each of them donate a certain number of valence electrons to it, or ammonia, NH3, right? Based on the periodic table, you know how many valence electrons each atom has. You just count them all up and they all just throw them in a pot and go bleh. All right, so now we're going to take all those valence electrons, try to achieve the octet and duet rules and the preferred number of covalent bonds. Go for it. Right? So it really doesn't matter once you're all said and done, once you got the pile, it doesn't matter what atoms they came from. Just total them all together. So, and this is key. This is huge. You have to know how many electrons you have to deal with to start placing them in there when you're putting it together. So all it is just the sum, the total number of valence electrons for the whole species is the sum of valence electrons for each atom in that species, right? Carbon puts in 4 into the pot, nitrogen 5, hydrogen 1, oxygen, right, 6, boom, easy, easy. But you have to watch out for the charge. You have to subtract the overall charge, because if it's an anion, say with a negative free charge, that negative free charge is because it picked up 3 more electrons. So if you subtract the negative charge, you end up adding those electrons to it. If it's a cation with a positive charge, that means you lost, right? So if it's a positive 1 charge, you're subtracting 1, which means there's 1 less electron. That's why it has a positive 1 charge in order to achieve octet and duet rules and the preferred number of covalent bonds. Ooh, right on. So for example, let's take ethanol, CH3CH2OH. So this is more of a, it's not a molecular formula. This is how an organic person might do it. But would you agree we have carbon, hydrogen, and oxygen in there? Well, let's total them up. How many carbons do we have? 1, 2 carbons. So what you do is you take the carbon, and you can just do this in your head. I have 2 carbon atoms, right? Well, how many valence electrons does each carbon have? Well, carbon's over here in group 4. 1, 2, 3, group 4A. So each carbon puts in 4. So you take the number of those specific atoms of that element times the number of valence electrons of each atom. So 2 times 4 is a total of 8. This carbon puts in 4, that carbon puts in 4. That's a total of 8. And then we have 1, 2, 3, 4, 5, 6 hydrogens. So 6 hydrogens. Well, hydrogens, group 1A, it only flings in. I'm going to fling in my 1 electron. So 6 times 1 is a total of 6. So each hydrogen puts in 1 for a total of 6. So now we're at 8 plus 6, 14, right? We have 1 oxygen. I'm the only one, and I got to put the most in there. This is not a fair game. So 1 oxygen times 6, it's the chalcogen. 1, 2, 3, 4, 5, 6. It's group 6A. So all of those put in 6. So we take our 14 plus our 6, which is a total of 20. This is a neutral species. So effectively, we're subtracting 0 from that, right? You can just do that in your head. So we have a total of 20 valence electrons. If that was charged, we'd have to take care of that. This is the easy step, but it's the one I tend to screw up the most. Once you know your total number of valence electrons, now let's sprinkle them in amongst all those atoms and try to achieve octet and duet rules. We can do that. Let's go to step 2. All right, this is where I'm a little more non-traditional, I think. This is the most, well, they're all important. You screw up one step, you're toast. Step number 2, we're going to calculate this term. Let me explain what everything is. 6n plus 2 minus the total number of valence electrons. Ooh, so what is everything and what does this mean? Well, we know what the total number of valence electrons, that's how many we have in the pot, right? That's from step 1. What is 6n plus 2? Well, n, capital N, is the number of non-hydrogen atoms in that species. So like for ammonia, NH3, well, it's got 3 hydrogens. We don't count those and has the nitrogen. So N equals 1. So 6 times 1 is 6 plus 2 would be 8, right? That term, 6n plus 2, which some people call the bond order, is the number of electrons required to have all single bonds in that species. All right? So essentially what we're doing, we're saying, okay, how many electrons are necessary for all single bonds? And how many electrons do we actually have? Let's subtract them. If those are the same, you'll get a value of 0, which means you have all single bonds. So yeah, there's only 3 possible outcomes. Either these 2 terms in brackets are the same, and you get a value of 0, meaning all single bonds. Or 6n plus 2 is bigger than the, you have, right? If 6n plus 2 is bigger than that, you're subtracting a smaller number, you're going to get a positive value. That has several predictive consequences from that we'll do on the next board. What if 6n plus 2, the number of electrons required for all single bonds, is less than the number of valence electrons? Oh my gosh, you get a negative value. That means you have more electrons than you need for all single bonds. What? Right? If it's positive, you don't have enough electrons to make all single bonds, which means you're going to need double and triple bonds. If it's negative, you have too many electrons, you're going to have expanded octets, things disobeying the octet rule. You might have atoms in there with 10 or 12 electrons around them if you have more electrons than you need for all single bonds. So it's great predictive ability. So what I want to do is look at, in turn, what if the value is 0? What if the value is negative? What if the value is positive? What does that mean, and what can you predict in your Lewis structure? Let's do it. All right, let's start with the easiest one. What if we do 6n plus 2 minus the valence electrons? Again, 6n plus 2 is the number of valence electrons needed for all single bonds. And the number of valence electrons is the number of electrons we actually have. If those are equal to each other, you're subtracting the same number. 8 minus 8, 12 minus 12 is 0. Which means you have exactly the number of electrons needed for all single bonds. Which means you have only single bonds in your Lewis structure. No double bonds, no triple bonds, no multiple bonds at all. No funky business. Nothing's disobeying the octet rule, right? Everything follows the octet rule. Hydrogen follows the duet rule. No funky monkey business. We love these. Right? You never see these on exams. Right? Pretty simple. Well, let's look and see what if we have a negative value. Ooh, and then we'll do, a bunch of examples and stuff. All right, this is one you probably didn't do in high school, maybe high school, it depends who you had, or introductory chemistry. We don't do expanded octets, at least when I do introductory chemistry, everything follows the octet rule. But the real world things get weird. Some things might have more than 8. Well, this allows you to predict that before you even start your Lewis structure. I love it. So if we do 6n plus 2 minus number of valence electrons, right, the number of electrons we need for all single bonds, and the number we have, if that's negative, that means we have more electrons than we need for all single bonds. Oh no, we got too many electrons, which means something's going to need more than 8. That's called an expanded octet. It's expanded beyond 8. And the negative value is the number of electrons beyond 8. So if we take 6n plus 2 minus the number of valence electrons and get a negative 2 value, well, that's 2 beyond 8, or 8 plus 2 is 10, right? And usually it's the central atom when you do a Lewis structure. Almost always the central atom is the one with the expanded octet. So you draw the octet with 8 electrons, and if that was a negative 2 value, you'd add 2 to 8, you'd have 10 electrons on it. That'd be tough to anticipate otherwise, right? What if I did 6n plus 2 minus number of valence electrons and got a negative 4? Well, that means 4 beyond the octet of 8. So 8 plus 4 would be 12 valence electrons on that central atom. That's some pretty cool predictive power. And I'm going to do an entire video just on expanded octet. So I'm not going to do examples here. I just want to go through the rules, get you thinking about it. And then we'll do a video for expanded octets. We'll do a video, what if you have multiple bonds, electron deficient species, yada, yada, yada. So you can focus on each one. So again, negative value, you've got an expanded octet by that negative value. Beyond 8. Remember, expanded octet is beyond 8. Boom! All right, this is the toughest of the three. Remember, if 6n plus 2 minus valence electrons is 0, we have all single bonds. No funky business. If 6n plus 2 minus valence electrons is negative, we got an expanded octet beyond 8 equal to whatever that negative value is. But what if it's positive? A little trickier. I'll show you how to do it. And we're going to do some videos for each one. Well, that means you don't have enough valence electrons. This is how many you need. Well, if the number of electrons you have is smaller than the number you need for all single bonds, you don't have enough electrons to have all single bonds. Which means one of 3 possibilities here. There's 3 things that can cause you to get a positive value. The most common one, and I'll put a star next to this, if you don't have enough electrons for all single bonds, that means you're going to have to collapse them in to make a multiple bond, either a double bond or a triple bond or something. So for every value of positive 2, so if you get a value of positive 2 here, means you're missing 2 electrons, you don't have enough. So what you do is you pop that in as an extra line to make a double bond. If you have a plus 4, that means you have 2 extra lines or 2 multiple bonds, which could be 2 double bonds or 1 triple bond, right? 1 extra line. So every positive 2 means 1 extra line. That's one possibility. And we'll do a bunch of examples for that. The second possibility is the opposite of an expanded octet, right? If you get a negative value, you have too many electrons, so you have something beyond 8. Well, if it's a positive value, that means you don't have enough electrons. You could have an electron deficient atom in your species, which means it has less than 8 electrons based on the positive value. So if you get a positive 1, that means you have 8 minus 1 or 7 electrons on some species. If you have a positive 3, 8 minus 3 would be 5. You have 5 electrons on something. If that's a positive 2, 8 minus 2 is 6. You have 6 electrons on something, right? So it's hard to determine, do you have a multiple bond or do you have an electron deficient species? I'm going to do videos to show you how to deal with that, all right? Now, another possibility is you have an organic ring, like a snake eating its tail. Remember we looked at line structures? You can have pentagons and hexagons and things like this, these cyclic hydrocarbons. They're pretty crazy, hexagons and octagons. Well, when you have a carbon chain, carbon, 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 that turns around and connects back to itself, in doing so, sucks up an extra pair of electrons and counts as plus 2. Right? I'll never give you anything that has more than 1 ring, but if you have an organic ring, so you need at least 5 or 6 carbon atoms to do it. We're not going to get triangles aren't real stable. Squares, I guess you could get, but they're not real common. So in my class, if you can get a pentagon or hexagon, 5 carbon ring or a 6 carbon ring in your species, I will not give you those on my exams, but in lab and homeworks, take a look at structure, and if that looks possible, if you get a value of positive 2 here, you could have an organic ring. What's even worse is, what if we had a positive like 8? Well, man, that means you could have a ring and 3 double bonds. Oh, right. I try not to combine these things. So on my exams, it's probably going to be a multiple bond unless it's got one of the trigger atoms for an electron deficient species, which I don't have room to put it in there, but I'm going to do a whole video just on electron deficient species, boron, beryllium, and aluminum, if you want to write that down. If you see boron, beryllium, or aluminum, those have a tendency of becoming, so there's beryllium, there's boron, those aluminum. They have a tendency of having electron deficient structures. You'll end up with 6 electrons instead of 8, or 4 electrons instead of 8, or 7, or something like that, right? So we'll do a whole video on that. But anyway, that's the tricky one. Let's move on to step 3. See, now with step 2, it allows us to predict what we have. Let's move to step 3. Step number 3, you just kind of do in your head. So now that we know the number of valence electrons we have, we've done 6n plus 2 minus the number of valence electrons to predict, do we have multiple bonds, organic rings, expanded octets, electron deficient species. So we kind of have it. We've anticipated what we have. What we have to do now is go, well, if I have a bunch of atoms, which ones tend to be in the middle, right? Well, they tend to be those are called central atoms. So a central atom is in between 2 other atoms. So if my head is an atom and there's an atom here, and we're bonded, it's in between those 2 atoms. So any atom bonded to at least 2 other atoms is in the middle. That's called a central atom. That's going to be the core. In the next step, we're going to draw the skeleton, the skeletal outline of it. We want to know what's the middle and what else is attached to it. Typically, those are the least electronegative atoms. What's electronegativity? Well, similar to electron affinity, but not quite. Electron affinity is an atomic property. Electron negativity is more of a bonded atom property, right? So electron activity is the attraction an atom has that's in a bond for those bonding electrons. So if I got 2 atoms bonded together and is sharing those electrons, how attracted is that atom to those bonded electrons? We're going to hit this pretty hard when we look at bond polarity later. So the trends of electron activity follow the electron affinity trends pretty closely, right? So remember, electron affinity was very favorable for the nonmetals and not favorable. They don't like the electrons. Same thing's true for electronegativity. So these elements that are higher up and farther over tend to have high electronegativity values, discounting noble gases, and these metals don't, right? So as you move towards the right, electronegativity increases, and as you move down, it decreases. So you can kind of look at that and go, well, from that scenario, fluorine probably doesn't want to be in the middle. You know what I mean? And these are going to form ionic compounds. So you're pretty much looking, as you move in here, the central atoms tend to be more over in this region. Carbons and nitrogens tend to be central atoms. Halogens are pretty electronegative. They don't like being central atoms. Hydrogen can't be, regardless of its electronegativity value, because it follows the duet rule. So 2 electrons makes 1 single bond. Hydrogen can only have 1 single bond. It can't have 2. So it can never be in the middle. So it's always terminal. I'll write that in there. So a terminal atom is one on the outside. It's only bonded to 1 other atom, which would be in the middle. Right on? So that's a way just to kind of think about what goes in the middle, what goes on the outside, central versus terminal. And sometimes you can have more than 1 central atom. So if you only have 1 central atom, it's called a simple molecule or simple species. If you have 2 or more central atoms, it's a little more complicated. So it's called a complex species. Next step. All right, this is the meat and potatoes of a Lewis structure, the skeleton. So the way I'm doing it, because we predicted multiple bonds and things ahead of time, my skeleton might be a little different than other methods. Most people just do the skeleton and just say only put single bonds in there. Well, the way I'm doing it with step 2, you already know if there's double or triple bonds or a ring. Well, we can put that into the skeleton. Right? So start with any central atoms, the least electronegative ones you can find other than hydrogen. Use the chemical formula as a guide. There's no perfect way of doing this, but this helps. These are guidelines. So if there's a molecular formula or specifically a condensed structural formula, right, use that as a guide for like where the hydrogens are and if that chlorine's connected to this carbon or that carbon, those kinds of things. Try for symmetry whenever possible. Nature loves symmetry. Try to avoid connecting two highly electronegative atoms. They don't like bonding to each other unless they're forced to. So like oxygen's very, very highly electronegative. Fluorine's number 1. Oxygen turns out to be number 2. They hate bonding. Fluorine does not like bonding to fluorine. Oxygen does not like bonding to oxygen. But if you have a diatomic element, it's unavoidable. And a peroxide, by definition, is an oxygen-oxygen bond, but it's highly reactive. Doesn't like to be there. It'd rather not be that way, right? So they tend to be pretty reactive. And then this is what my extra stuff is. If you know there's any multiple bonds, because you did this in step 2, the 6n plus 2 minus number of valence electrons, and got a positive 2 value, you have a double bond in there. Figure out where that double bond is. If you have a positive 4, you have two multiple bonds. So you could have 2 double bonds or a triple bond. Figure out where they go based on the preferred number of covalent bonds. Remember how to predict that. It's the number of columns away from the noble gas. So oxygen prefers 2 covalent bonds. So all the chalcogens prefer 2. Halogens prefer 1. The pnictogens prefer 3. Carbon prefers 4. Silicon prefers 4. So you can give it its preferred number of covalent bonds if you have multiple bonds to place in there. Yeah, right? So let's do an example real quick, and then we'll go to the next one. So let's do one quick example with the ethanol we did earlier, right? So we'd already done the number of valence electrons. We don't need to do that again. So we know with ethanol, CH3CH2OH, we had 2 carbons, 6 hydrogens, and 1 oxygen. When you added them all together, you got 20 valence electrons. It's neutral, so we didn't have to worry about the charge. Well, let's calculate the 6n plus 2 minus number of valence electrons. So n's the number of non-hydrogens. So we don't include the hydrogens, so we have 2 carbons, and an oxygen, so n equals 3. Right? So n equals 3 here. So 6 times 3 is 18, plus 2 is 20. 20 minus 20 is 0. Well, what does it mean when that's 0? That means we have all single bonds, because 6n plus 2 is the number of electrons required for all single bonds. We happen to have that same number of electrons, so there's no double bonds, no triple bonds, no expanded octets, no carbon rings, organic rings, no electron deficient species. Everything's perfect! Yay! I like to combine steps 3 and 4. I just look at that and go, carbon's less electronegative. Hydrogen can't be central. Carbon's a lot less electronegative than oxygen, so the carbons are always going to be in the middle. But let's take a look at this here, right? Use the formula as a guide. So take a look here. You see the reason they split the hydrogens up? What this means is those 3 hydrogens are on that carbon. You see that? So let's draw that. Let's draw that first carbon and draw 3 hydrogens. Now there has to be a minimum of a single bond, and you could use 2 dots if you wanted to on there. So you have to at least start with a single bond. Now there's no multiple bonds, so I don't have to worry about double or triple bonds. I know that ahead of time. So this must be connected to that next carbon. That's why we drew it this way. And you see those 2 hydrogens there? Use the formula as a guide. Those 2 hydrogens are on that carbon. That's why they were drawn there. And you can do them on top, bottom, right, or left. Doesn't matter. But I like to work it left to right. Hydrogen has to be a terminal atom. So I don't want to stop it on the right, and then I have to start going down and all over the weird place. I like to meander my way left to right. Now, this carbon is either connected to the oxygen or hydrogen. But to see the way that's written, this hydrogen is bonded to that oxygen, which means the carbon must be bonded to the oxygen, which is bonded to the hydrogen. See that? So that's a pretty highly electronegative element, but I couldn't have the hydrogen in the middle because hydrogen can't be central. So it has to be this way. You see that? So, and there's no double or triple bonds, anything like that. This is my skeleton. So obviously in the next step, we're going to complete the octets, aren't we? Hey. So if I had double bonds, if I had multiple bonds, I'd put them in there to get the preferred number of bonds. See, carbon prefers how many bonds? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Isn't that nice? Hydrogen can only have 1 bond. 1 bond, 1 bond, 1 bond, 1 bond, 1 bond, 1 bond. Oxygen prefers 2 bonds. 1, 2. Oh, it's perfect. Let's go to step 5. Right? That's a guide. This is your number 1 guide for drawing the skeleton. Trust me. All right, next step. Now we in step 4 we drew the skeleton, right? And we had any double or triple bonds that we predicted in there. Next step, we're going to complete the octet rule for all atoms other than hydrogen. Remember, hydrogen's the duet rule, so hydrogen's set. And we're going to complete the octets using lone pairs. So we're just going to say, oh, that's only got 6. Pop a lone pair in there. That only has 4. Pop 2 lone pairs in there. Just add lone pairs until everything has 8 other than the hydrogens. Now, if in step 2 you predicted an expanded octet, something will have more than 8. Take care of that here, right, with lone pairs. If you had an electron deficient species, something with 6 electrons or 4 electrons, it's got less than 8, we have to account for that here, right? But you can predict for that. You already know that ahead of time from step number 2. Woo! So let's take ethanol. This was our skeleton from ethanol. Let's check the octet rules. Now hydrogen has 2, 2, 2, 2, 2, 2 right here. So each line is 2 electrons. Let's check the carbon. 2, 4, 6, 8. So that carbon already has 8. Octet rule satisfied. We're not going to put any lone pairs on that because that would give it more than 8. This carbon has 2, 4, 6, 8. You're going to find that's true for carbon because it likes 4 covalent bonds. Well, 4 covalent bonds, 2 electrons per bond, that's 8. Carbon doesn't like lone pairs at all. Pretty rare. This oxygen has 2 bonds, so that's 2, 4, which is not 8. Correct? So if we have 4 but we need 8, we need 4 more electrons, which is 2 pairs. Nanu, nanu. Right? So I'm going to add, I got 2, 4, 6, 8. That completes the octet for the oxygen. You see that? So these are my lone pairs. So you just slap on lone pairs to complete the octet. And if you have an expanded octet, put more on there. So if you're supposed to have 10 or 12, you got it. If you're only supposed to have 6, make sure they only got 6. Last step. And then we're going to do multiple videos on different examples. All right, last step is just kind of an obvious one. A lot of times we forget it if we're in a hurry on an exam. Just like, oh, okay, I hope it's good. So check the Lewis structure. So here's some things I want you to look for. Make sure every atom in the Lewis structure has the octet rule satisfied, except for hydrogen, which should have the duet rule satisfied. Unless you predicted in step 2 an electron deficient species or an expanded octet. So double check that. And if you had any multiple bonds predicted in step 2, say you predicted 3 multiple bonds, make sure they're in the structure. Okay, so it always has to, so step 2, your 6n plus 2 minus number of valence electrons has to match the Lewis structure you drew. I'll always give you points. Even if your Lewis structure is wrong, if those are connected, at least I can give you some partial credit. You predicted 2 double bonds, you got the 2 double bonds in there, maybe you messed up another part. I can give you some partial credit, right? Make sure, this is a necessary thing, the total number of electrons you used to write your Lewis structure to get expanded octets and electron deficient species and multiple bonds and octet rules, count up the total number of electrons that you used to do that had better equal the number of electrons you calculated in step 1, because that's how much you have in the pot. Right? You can't use more or less than that. That's how many you have to achieve all of those goals that you predicted in step 2 in the octets. And this last one is not concrete. Double check that those atoms, those elements have their preferred number of covalent bonds, ideally, but that's not concrete, right? Oxygen would love 2, but I've seen it with 3. I've seen it with 1. Nitrogen likes 3. I've seen it with 4, right? So it's not a perfect rule, but it's preferred. Let's check it for the ethanol one we did on the next board. All right, for the ethanol, CH3CH2OH, or you could go C2H6O if you wanted to, which remember that had 20 valence electrons from step 1, 4 plus 1 plus 1 plus 1 plus 4 plus 1 plus 1 plus 6 plus 1. And here's the Lewis structure that we determined, right? We had the 3 hydrogens on the first carbon, 2 hydrogens on the second, oxygen with a hydrogen bond to it, and we needed those 2 lone pairs on the oxygen to complete the octet. We did not predict, remember step 2, 6n plus 2 minus the valence electrons was 0, so all single bonds. No multiple bonds, see that? We did not predict any double or triple bonds, no multiple bonds, they better not be in there. We did not predict any electron deficient or expanded octets. So everything should follow the octet rule except for hydrogens with the duet rule. So there's 2 on the hydrogen, 2 on the hydrogen, 2 there, 2 there, 2 there, 2 there. All duet rules satisfied. 2, 4, 6, 8, octet rule satisfied. 2, 4, 6, 8, who do we appreciate? Octet rule satisfied. 2, 4, 6, 8, octet rule satisfied. So all octet rules are satisfied. So all octet and duet rules, they are satisfied. Satisfied. So that's good. Let's count up the total number of electrons we used to satisfy those octet and duet rules, and that better equal 20. You ready? 2, 4. Remember, a line's 2 electrons. A single bond's 1 pair, right? 2, 4, 6, 8, 10, 12, 14, 16, 17, 18, 19, 20. Yay! Happy face. All right, if that wasn't 20, I'm screwed up somewhere, right? And how many bonds does carbon prefer? 1, 2, 3, 4. 1, 2, 3, 4. Hydrogen prefers 1, oxygen prefers 2. This is a perfect Lewis structure. We're going to prove that with formal charges later. Let's do tons of examples next on new videos.